So we're now actually recording. So my name's Andrew Livingston, if we've not met before. For those that we have met, that's good. Now, it's a slightly different module to what you've had with me in the past. And probably going forward as well, any other time you have myself as a lecturer on any of your modules, they'll tend to be more mathematical or more technical based. This module is no different. We got asked a question before we started recording. How does this module differ to part 1 of the module from first year? There are some differences, but there's an awful lot of similarities. Do you need to have studied the previous module? No, you don't. We'll go through what this module is more about, even though it's called part 2. It's called part 2 because primarily we're looking at different materials. We're looking at materials that are more complex than concrete or steel, but it's not all about concrete. It's not all about the material selection of timber. It's also about where these wonderful equations come from. Now, I'm not going to manage to record. I'll just hand the books out, that's what I'll do. So, I quite often say to students, don't go out buying textbooks because you've got access to them all in the library, physical and digital. However, there are some books that I do recommend that you buy. There's not many of them. This is one of them. This is a relatively new version. It's the 3rd edition of the Structural Engineer's Pocketbook. The reason why I recommend this is it's an encyclopedia of all sorts of nice things in there. Now, you don't need to go out and buy it now. You can get a digital copy of this. But when you go into practice, hi, how you doing? Try and move some chairs around and find somewhere to sit. Yeah. So it's a good book, right? And I'll give you an example why I think it's a good book, not why, but to demonstrate that I do believe what I say. This is my version of the same book, but the 2nd edition, when I used to be a full-time in-practice engineer. I'm still working practice just now, but I work under the auspices of Edinburgh Napier, so I'm still building real buildings as we speak. We've got ongoing projects, but when I was full-time, before I came to Napier, this used to be on my shelf in my office. I've got many books, but I'm a bit of a hoarder when it comes to books, but this is my one I used to use quite a lot, and you can see it's falling to bits, pages falling out and everything. So it's quite a handy thing. So why am I talking about it today? I'll use this one. You can see my tags that are falling to bits. You've got all these equations. Can you see these equations? These guys have seen them all before. The equations for a simply supported beam with a point load in the middle. You've all done that last year. And you've got a bending moment. It gives you the reactions, it'll give you the bending moment maximum and the maximum deflection, and it'll do that for all different scenarios. Yep. So these are wonderful little equations, and what we'll be looking at today, all different times. What we'll be looking at today, not today, all we're looking at in this module is where all this stuff comes from. I'm sure you've seen this before. I'm sure you have. Like these sorts of things, these equations here. And you're just given them, and we use them like a pocketbook, don't we? So what's the equation we need? There's the equation, we use it, doing hand calc nice and easy, but we don't give much thought to where they come from. Well, today, not today, this module we do. Before we can even do that, we need to think about what's happening within the material. Before we can even start to prove any of this. So we'll only start to prove some of this stuff at the latter end of this module. But between now and then, there's quite a lot for us to understand, get to grips with. There's an awful lot of, no, there isn't that much, to be honest. I'm making it sound really difficult. It's not. It's actually quite simple. But there are some mathematical notations you'll have to get to grips with. So on our middle page, we are CTR08108. Before we go any further, this is a nice image that I stole from one of my colleagues. I work at a research centre about 5 miles from here, and my colleague's in the same building as I am, or same department, sorry. We are Wood Science. It's a boring name for a department, but that they're called Wood Science. Anyone understand what this might be? One more time? Wood, yeah, wood, but a bit more about detail.
Like under a microscope or something?
Under a microscope, yeah, it's 1 year's growth.
Is it the cell walls?
Yeah, that's exactly it. It's exactly. It's a nice little image. We'll come back to that later on when we talk a bit more about wood. But for just now, we're not even going to consider wood. We'll stick to just generic materials for today and for the next several weeks. So, look at the middle page now. Middle has changed, and it only changed a few weeks ago. So I'm still getting used to it myself. So I apologise. But my content's still my content. My email address there, my email address is there. What I will do is I'll put up a folder within Moodle giving you what's called office hours. I haven't decided yet when they're going to be, we'll decide that today. Office hours will be a day of the week that I know that you'll be on campus. I know you're on campus on a Monday, but what other days are you on campus?
Wednesday, Thursday.
Oh, you're in Monday, Tuesday, Wednesday, Thursday.
At the semester, yeah.
Oh, you've got quite a lot on then. Right, okay. So what we'll do is we'll pick an office hours based upon you guys and my other modules. Monday might be okay for me actually. Can you get any classes after this class? All you've got is just me today.
Later in the semester, later in the semester we seem to have more. I think we've got 3 classes on Monday later in the semester.
In like 3 weeks' time, I think we have 3
an extra one.
classes.
I think it might be you again.
I think it's all me.
Yeah.
We'll talk about my stuff later on. Yeah, we'll get there, right. So I think what we'll do is we'll do office hours on the Monday. What just essentially means any questions at all, and it can be related to the module, or you should all have PDT lecturer, PDT tutors. Some of you might know who that is, some of you might not. Some of you never even want to talk to a PDT lecturer, but if you've got any questions, it doesn't need to be about the module. It could be about your student housing, or it could be anything if need be. But if you want to have a chat with any of the lecturers, we're all open to do that. You do have PDT tutors to say you want to ask questions that are totally unrelated, or it could even be that Andrew Livingston, he's not listening to me, or he's picking on me in class. Hypothetically, of course I'm not going to do that, but there's somebody else you could talk to independent of your lecturers who don't teach you or shouldn't be teaching you. So you should know who that is. If you don't, I can talk to you and I can help you find out how to identify who your PDT is. But yeah, open office hours is essentially come and talk to me about anything, or even if you're stuck on some of the coursework or some of the things to do with this module, that's the time to do it. Okay? Or in class, just shout out, because if you're stuck on something, I'll guarantee it, so are some other people. Right? Don't assume that you're the only one if it's a module related question. Nice just to ask. Right. Well, I will have office hours opened up. So let's talk about the teaching material. Oh, sugar. I never checked these links. No, they're emails, they're fine. They're all fine, yeah, so I did check the other ones, right? So these emails here, these are just some helpful emails. You can talk to people if there's things you need to have a chat with them about, and it's self-explanatory. Let's have a look at our teaching timetable. Our classes are 9:30 to 11:30. Obviously on a Monday there's the dates there. There's a thing called a reading week on week 7. This has caused me a bit of a problem for this module. This module used to be try 1, now it's try 2. I think we've got people that are from GAs.
I think they're on Thursday.
They were on last trimester.
Alright, okay. So my module used to be Try 1, it's now moved to Try 2 to facilitate something to do with GAs, which means I've lost a week of teaching. What I used to do was a thing called like a group activity, and you had to do a bit of research, and it would take you a week to do it, and you had to do a presentation. So we'll come to that maybe later on this morning. We'll decide we want to put that back in. But if we put that back in, then I'm going to have to lose a mock exam. You either have a mock exam, or you get the formative assessment. So we can talk about what those two things would look like, and I'll be honest, it'll be up to you what you want. So our classes, there's titles there, but there's also, as you were saying before, there are some weeks that we've got additional things. Now we've got laboratories, which they're compulsory. You have to be there, right? They're quite cool. They're going to be down in the A25. Thankfully, they're all on the same day, so it's the Monday, so it's not too bad. You're already in class anyway, and this will be you witnessing the actual lab test that you'll have to do your report on. Now, the tutorials, these are not compulsory, these are optional. So your coursework will be mathematical, and they'll be using a lot of Microsoft Excel. And it won't be basic Microsoft Excel that you've done before in high school. It'll be a little bit more advanced than that. And those tutorials are for you to do the actual coursework and for you to get help. And now, they're not compulsory, but I have pre-prepared material for them, if that makes sense. So I'll be showing you tools that you probably never knew existed before, which you might need. And it's all on the same day, so it's all on the Monday, so you're already in class anyway, so it's well worth your while just to hang around, get some lunch in between, then come to the tutorial. It's well worth it. And if need be, I can put more on, but what I don't want to do is to repeat what was on, say, week 4 on another week, just because you didn't turn up in week 4. Try and turn up, because there is pre-prepared material for these, especially the earlier ones, especially these two here. I will try and not miss those two. Okay, so that's the timetable. Come to the assessments, sorry.
Just seeing the compressive test bit, are we going to be using the Crush Lab then? Are we going to be using Crush Lab?
Crush Lab? Oh, we're doing something better than that. Well, no, so you were using the Crush concrete cubes last time, weren't you? So they were using concrete cubes or cones?
Week cubes and week
Slump test. I heard your slump test failed dramatically. What a slump test is?
Yeah, I went to college before this, so we did cubes and slump test as well.
Yeah, theirs was failed dramatically. It's beautiful. It's what you wanted to see. But so we're going to be looking at different types of testing. So we'll talk about that just now. So your coursework, you'll have to analyse data from different types of testing, and we'll discuss later on in weeks what those exactly are and what the code is you'll have to follow, and you'll have to write it up as a formal test. However, because I said before that I work in the industry as well as within Napier, we do commercial testing. We've actually got commercial testing in a different facility that's about 5 miles away from here. What I'm thinking about doing is having you sign up to go to, it wouldn't be a Monday, it would be a separate day of the week. Sign these up and we could take you to a laboratory down at Seven Hills. Anyone been taught by Wojtek before? So Wojtek has got some commercial testing down at our office down the road. I'll be showing you that. I think he's got some rather large beams. It'll be the same test as you'll find on this one here. The same test as that, but rather than having a sample that's that size, the sample will be, me away. be that sort of size, and it'll be in a very different machine. I hope it's the big yellow. We've actually got 3 machines down there we can test it on, very similar to when you use the crushing test for cubes. We've got one that's a big yellow, massive 8 meter thing that's really quite big, but we've got a brand new machine. It's not even commissioned, installed, not running yet. It's absolutely brand new. I'm hoping it's on that machine. That's quite nice. I've seen a similar machine being used before. And if we do that, we'll also look at other methods of grading of timber whilst we're there. I've got a machine that I bought a few years back, about £10,000, for doing acoustic grading. So I can show you, well, not show you, you'll get to actually physically do that as well at the same time. Maybe a few other things as well we can do whilst we're in the lab. Right, so this is our timetable. Then we've got some recommended reading. Right. Okay. I'm not expecting you all to go to the library and get a copy of all of these books, or even a digital version of all of these books, but a lot of the material that we have will already be talked about within these books. So if you want additional material, you don't quite understand something I've explained, and you want somebody else to explain it to you in a different way, these are some lovely books that'll do that. Hi, come in. Mate, you okay? Let's try and get a table and a seat. Right. So, however, what I would say is this module is self-contained. So let's just say you didn't look at any of these books, you'll be absolutely fine. It is self-contained. Right. Whilst I'm on that, if your mathematics isn't up to speed, this is something I do recommend. I've given you this book. I'll show you just in a second where this book is on digitally. I've given you a PDF for you, so do not go out and buy it. It's about £60 you don't need to buy it. I've given you the PDF. Download the PDF. Keep it for the rest of your. I'm going to be honest. Keep it the rest of your life. It's the mathematics you'll need from now to beyond the PhD. It's all by example. So for those that are doing mathematics, you're doing mathematics?
In maths,
yeah. Now, my problem is how we teach maths here. I think it's very good. My problem is how we teach it here is that you get lumped in with other people, other disciplines, mechanical, acoustic, electrical engineers, and you're all learning the theories. Now, last year you were getting complex numbers, calculus. In first year, yeah? You'll need that for this module, right? You'll need that for this module. And those, what you're learning this year in mathematics, have they told you? You're going, no, I don't care. Maths.
I looked online, but I forgot.
Yeah. So there'll be things you'll be getting taught. You will, those mathematics. Now, somebody said to me last year that third year mathematics was not required. And then another student turned around and said, well, wait until you get to fifth year and you start doing FEM, finite element analysis. Then you'll need all of that matrix manipulation. Then it'll become very, very, very relevant. Right, it'll be compulsory, in fact. So the mathematics is important. I would say, though, if you're anything like me, if you asked me to do calculus right now on the board, I would struggle. Because I use it infrequently. But as soon as I look at a book, actually, calculus is in here. All the stuff that I need is in here. That's my go-to handy book. But this book here will give me worked examples of not just calculus, but anything you want. And it takes you from, like, not quite primary school maths, but high school maths. It'll take you from high school maths all the way through. It's very, very good. And you've got it free of charge anyway. Keep it. I will be using bits of that book. I'll be giving you extracts of it as well. But download it. I'll show you what it is. Ebooks. So it's this one here. Download it and it's yours. Just keep it. It is very handy. Right. Keep going through the module just now. we've got a module guide. I'm not going to take you through that just now. It's for you to read it later on, tell you a bit more about the module. I think I've pretty much covered, or I will cover most of it in this lecture. Yeah, so I'll tell you how the module's set up, where your grades come from, but I'm going to talk to you about that anyway. So there shouldn't be any questions about, oh, I didn't know where my grades were coming from, and I didn't know how it would get marked. This is in there. I'll give you a lot more detail verbally in a few seconds. And then my first extract from this book, I'm advertising it, but don't buy it. Well, buy it if you want, but you need to, is I remember when I first got the book, I was so excited. I thought, this is really good. My first years need this, my second years need this as well. And I just wrote some of the basic stuff out. This for mathematic manipulation. You should already know this stuff, but quite often you forget if you've not used it in a few months. So this is just a quick summary of how to manipulate equations. This class, you'll have to do a lot of that. You'll have to manipulate things. I'm going to show you my techniques that I use. I'm quite dyslexic, so I do things in a graphical way quite a lot of time. So I'll use this sort of thing, but I'll do it in a graphical way. I'll show you my method. But I'll put that down there just in case you want it. Right. Okay, let's have a look at today's content then. Two lecture slides. We've also got notes that I've given you. If you've got your iPads and you can go into Moodle, you can download those or have a look at those notes just now whilst I'm giving a lecture. If you haven't, don't worry. I've got you covered. It's fine. We'll just do the intro. I've already covered most of the stuff in the intro, but we'll do it in a bit slower detail. Just for those that walked in a bit late, we're actually recording today's session, so if you don't want to have your voice recorded, just raise your hand, I'll pause, then you can... I'm sure it'll be fine. Slideshow from beginning. It's only a few slides. So yeah, this module is Materials 2, as we said before. We will be looking at timber in some detail, but you won't be doing that till later on in the module. We're going to start off with generic materials, just so we can understand the concepts of it. Learning outcomes. These are your learning outcomes. There's only 4. By the end of this module, you should at least understand or be able to have that. This is your teaching timetable. Probably a bit easier to read than what I showed you 2 minutes ago. Right. So you have some courseworks and you'll have a final exam. Okay. Your courseworks will be presented there. That's your first one. We'll talk about the method, so the actual lecture itself will tell you how to do everything you need to do. Complete the coursework. It'll actually give you the document that will give you what you have to do as well. You won't do the actual test for that until week 6. So you'll have had a week of looking over the document, understanding the mathematics. You'll have downloaded the British standard, the European standard, BSEN 408. You will have done that, guys, please do it. Because when you come to the lab, there'll be questions that you'll need to ask. Questions that I'll probably not have covered in the class. So I'll give you one example, yeah? The conditioning of the material. How was it conditioned? I won't know that. I won't know that until I've got the actual samples and I'll know what the conditioning of it was. But you'll have to ask, and that's just one, there's many questions you'll have to ask that you'll have to report on. When you do a report, you're not just making it up. How do I do a report and you just make it up? No, you have to follow the British standard, BSEN 408. It will tell you exactly what you have to report on for you to give a report. Now, maybe I'm using the wrong word. We use the word report in English to mean different things, don't we? So when we do a report for a coursework at university, we think of, right, abstract. Right, we put an abstract in. We've got a literature review. We put a literature review in. And we already have our preconceptions of what a report is. So maybe I've used the wrong word. What we are doing is a lab test report. Very different thing. So you're not doing a normal report as what we would traditionally think of as literature review, abstract literature review, method statement. Not that. Not what you learn in CTR08108, Mark Taylor and Dan Ridley Ellis, when they would talk about how to write a document, how to write a report, didn't they? I've got one nod, excellent. So they did, I'm thankful somebody did talk about that. But this year's a lab report, so I'll give you, our BSEN 408 gives you exactly what you need to do, and it literally gives you the format as well. So I'll talk you through that. So that lecture there will tell you how to do it. That's the date for the test for that one. And then the week after that, I'll give you the lecture on the next test and the last test. I'll tell you how to do the final two courseworks, but you won't be given the actual coursework information until after you've submitted. So the submission date for coursework 1 is the day before, so that'll be Thursday rather than the Friday, yeah? So you'll submit it on the Thursday, then on the Friday I'll give you the next coursework to do. They're not big coursework, they're really short and sweet. So I'm not looking for 5,000 words. It's quite literally a lab report. So it shouldn't be a big scary exercise. Especially if you come to the tutorials on the Excel, then this will become fairly straightforward. I say fairly straightforward. The Excel will be a lot more than what you've ever done before, one would imagine. So do come to them. Now, so the submission date for the first one, submission date for the second one, and the third one, they're all on the Thursday before the Friday lecture. And the reason why you've got 3 of them is in the past, when I've done this, I'd have that as just one lab report. I'd leave it to the end of this sort of time, when you've got 2 other modules, and you also had courseworks to do for them, and you had exams to prepare for, and it was just too much. So the whole point, I'm hoping to get good feedback from this, is that we're breaking the coursework down to simple bite-sized chunks. That's all we're trying to do, okay? So don't go, oh, too many courseworks. Well, if it was the other way around, you'd be harder coursework or too much to do at the very end. So I'm doing it for your benefit. Right, okay. We do have timetabled in here an experimental lab. This is in A19. This is purely a fun thing. I believe last year you got taught the Macaulay method. Excellent. So we've got, did they take you to that lab? Probably not, no. We've got some really cool experimental equipment, and it's all digital based, and it's cool. You can actually try out some of the mathematical things that you've been taught, but in real life, and get to see if your answers are correct. So what I'll do is I'll set for you some simple exercises. The Macaulay method is my favourite one, but there's about 3 or 4 that I can do. And we'll set them up. We'll break the class up into size of about 4 people, 5 people maximum. And we'll take you through just half an hour, but you'll have to have done the work before. It won't take you long at all. And then that will hopefully reinforce some of the mathematics that you've learned from the Macaulay method, and some of the stuff you'll be learning from what we're doing in this module. And also, did you do any 2D frame analysis with Wojtek or with Juan? doing 2D analysis at some point, so I can maybe show you some of that as well. It is really quite cool, and if you've been trained on it once before, you don't want to go back and use the equipment again. It is quite interesting. So my choice for you then, say that I've lost a week there, and because of that I've taken out a formative assessment that I would normally do. So what I am going to do, I'm going to give you additional tutorials most weeks. I'll even give you one this week, but I'll not ask you to submit it. But from next week onwards, I'll ask you to submit your formative assessments, totally voluntary, so you don't have to do it. But if you want to do it, I'll give you feedback on what you've written. So if you do the formative assessment, I will give you feedback for it, and that's your opportunity to get early feedback on how well you're doing. Okay? I can do that, absolutely. Then if we leave that in, what I can do here, either swap this over, right, and move that to week 13 and put in week 12 a mock exam. I can do that for you. Would you want a mock exam? Or just stuff it, just nail it anyway, just do the exam without any mock? What do you think? Right. Let's do that. That's a good, is it unanimous? Right. So we'll do that. I'll switch this over. I'll put mock exam there, and I'll put that to there. And this experimental lab is voluntary, but I would say it's actually really good fun. And then separate from this timetable, once I know from Wojtek when he's doing his lab tests, I'll figure out when it would be suitable for you guys to be taken down. Or it might even be on a Monday, in fact, probably better on a Monday. Take you down and get a whole bunch of taxis. Take you down with a bunch of taxis, do the test, do the other stuff we want to do down there, and get the taxis back. At Napier's cost, of course, we wouldn't ask you to pay that. We could do that. And I can try and arrange it for a Monday, depending upon these tutorials, of course. Have a chat with Wojtek, okay? Right. So, your assessments. Formative. Formative just means it's just for your own personal feedback. So that's those things that we're going to give you each week from next week onwards. I've got some for today, but I think we'll just go through it manually, depending upon our time. But then your summative assessments, which means essentially your marks. These coursework are worth 10% each. However, you still have to pass them collectively. So you need to get a minimum of, I think it's like 40%. You need to do, so you have to submit. You have to submit them. But they're only worth 30% overall, so don't freak out. Don't treat each one of them as if it's a dissertation. It's not meant to be. When I give you the handout, I'll give you exactly what your limitations are and how long it should take you to do it. It shouldn't take you, more. Once you've got the hang of the first one, the rest will take you one night, and that's it. At one night, finished. Get the first one correct. The first one should be fairly easy as well. The only difference is the mathematics is slightly different. Once you get the report formatting correct, and you know what you're meant to be doing, then it'll all be good. Right, your class test, it'll be worth 70%. Your date of the class test has not been determined yet. Traditionally, it will be in those weeks there. I think what we'll do though is, I think we'll make it a Monday. I'll have a chat with you maybe next week once you know what your other classes are doing. Because I generally don't know what your other classes are doing. And it might be you've got a class test there. Well, we can do ours there potentially. What are your other modules, just so I know?
Mechanics.
Mechanics. That'll be James Lake. That's good. Right.
I think it was meant to be, but it's a Vicky Demetria.
Possibly. Vicky's alright actually. Vicky's really good. Of course they're all very good. James is excellent as well. So, sorry? Right, cool. Well, we'll figure out. I don't want to have an exam the same day as Vicky's exam. The same week, sorry. I don't want to have them the same week. So we'll switch them about so we've got one week, one the other week. If that's okay with you? Right. Okay, let's crack on.
Do you know the exam for this one, by the way?
Sorry?
Do you know what kind of format the exam for this module is?
Yeah.
You will, yes.
Yeah. Not ready yet, but yeah.
I'm just wondering, is it sort of come in, sit somewhere, 2 hours, there you go, or is it sort of, on the computer, or is it...
No. It's going to be all done by hand. The scaries. Let me ask a question, right? If you don't want to answer, come and talk to me afterwards, right? But sometimes, or for example, I'll talk about myself then, right? I find it difficult I've got short-term memory problems, right? Terrible. The guys who've had me before, they know that. They know my short-term memory is shot. Like, trying to remember names is impossible. So I find it difficult to remember equations. Yeah, I genuinely do. Hence why my old book is falling to bits, because there's loads of equations in there. Easy to look up very fast. However, I am toying with making this a closed book exam. I think it's good to do that. What a closed book exam is, and I have to give you things that you might need. Might not give you everything. If I do make it closed book, I'm going to give you a document. Give you a document that will have what I think you'll need, but there'll be things that are not on there that you'll just have to know. So you'll be given that document several months, a long time beforehand, way before the mock exam as well, so you'll know what you'll have to just remember. Okay? I'm not going to make it onerous. However, if you've got a problem with that, talk to me privately afterwards, do it today, and we can figure it out. But yeah, it's going to be a sit-in class, face-to-face, pen and paper, calculator, no mobile phones, no laptops, iPads. That's how it will be. I quite like it that way. I'll give you my reason why I like it that way, is up until I joined Napier, I was a structural engineer for many years in practice. It was fine. I was going to be well protected, but when I would go into big meetings, it would always be meetings with other people with different disciplines, and I would be one of two engineers only in that big meeting. And it's fairly easy, I can say whatever I want, no one's going to pick me up on it. But when I joined Napier, I find myself on several occasions now where I've been in a meeting with seven of us, we're all engineers, slightly different type of engineers, but all structural engineers. Some are looking at cladding and facades. On one occasion, I wasn't interested. We were looking at, the Dyson building I've shown you before. They've seen it, don't worry about it. It's some project for James Dyson years ago, and it was a mass timber building. Other engineers at this point had moved on to a subject that I had no interest in. I wasn't responsible for it, and they were talking about the cladding of the building. However, they had posed a question earlier on that nobody knew the answer to. Well, I'm quite good at mathematics, I'm quite good at doing stuff. I'm quite good at working out where the load pathing would go. So I just sat and done it all by hand for about an hour and a half. And by the end of it, it was all handwritten, it's all scribbly stuff, but it was fine. Then eventually, like several months later, the people who were ultimately responsible for load pathing, because I wasn't, I was only responsible for the superstructure and the mass timber. I wasn't responsible for load pathing, the foundations or the metal work. So, but when the people who did do the load pathing, they came up with pretty much the same answer I had. I've done it by hand, and they had used £10,000 worth of software they had used. So, having the ability to just very quickly work stuff out is actually really handy. And it also means that people then go, oh, sugar, he knows what he's talking about. They know what they're talking about. So it's really good. So it's actually quite handy. So several times I've sat in meetings, you ask a question, and other people would have to go to a computer and work it all out. I didn't. I could just go and do it. And it makes me look good. That's the difference between an engineer and a software user, in my opinion. If you can't do that, you're not an engineer. Okay, that's biased of me, but I think you should be able to do that, personally. Let's go to our thing. Right. Okay, this is just the title page, and you can see the text. You don't need to read. You don't need me to read it out to you. We'll be looking at it later on. I would say though that we don't actually know if this is a painting of Hooke himself. I think it is. But it could also be this guy as well. We don't know. Right. So in this lecture or unit, we'll be looking at the tensile test. So we're not looking at wood at the moment. We're looking at just generic material. So it can still be concrete or steel. Right, a homogeneous material, meaning a material that's all the same constantly throughout. Actual load displacement relationship. Okay, so I'll not read through that word for word. Let's go to our first example. And how are we doing for time? We finish at 11:30, yeah? Perfect. We'll be absolutely fine. So we've got a bar. And it's under tension. But before we put any tensile load on that bar, we know the length of it. Okay? If I put a tensile load on that, I would expect it to get a little bit longer, wouldn't you? Now, it might not become like plasticine and get visibly longer, but in actual fact, it would to an extent get longer. Now remember, what we're trying to do here is we're not going to get like 50 odd mil extra in length. At some point this material will just rupture and fail. But remember what we're trying to do. We're trying to understand the mechanics of the material itself. Okay? So for just now we're only looking at tensile mechanics, not the bending. We'll come to that much later on, but just the tensile forces. Use the term delta to describe the additional length. Perfect. Just wanted this. Right. So the actual load displacement relationship, F force equals K divided by L, L being the length, and delta meaning the additional length gained. K, don't know what K is just yet. We get to that. So the elongation, delta or elongation or shortening, because it could be compressive as well, that is just L or Li, take away the original length. That's all it is. Li take away the original length. And then if we just acknowledge that K, which we don't know what K is yet, divided by the length, is the axial stiffness of the bar. It does make sense, doesn't it? Because in relationship to force, we've got the delta, so KL is just essentially it's the stiffness of it. How stiff is it? The stiffer it is, and the less movement you're going to get. The less stiff it's going to be, then we'll have more movement. So for just now, we're acknowledging we don't know what. I should have a little doofer. Let's see if my doofer works. I like my toys. Obviously not today. Right. So I fine, I'm going to hang a load from this, and I'm going to increase that load in similar to the machine that you were talking about before, the machines that apply a load. I can control my load, then my displacement will change. So function force by displacement defines the relationship between the load, and of course it does. And there's that equation there. Now you notice it's not linear. Would you agree? It wouldn't be a linear curve, would it? It would be slightly non-linear. Okay. However, we were trying to simplify something down so we can understand it better, we can communicate about it, and we can also put an equation to represent it. So not quite often, what we do full time is we have to take a complex scenario and simplify it down that it fits something we can actually manipulate and control. So from this equation here, call that equation 1, we can manipulate that. We can say, right, K delta 0, there's delta 0 there. The relationship is simply that. Right? Fairly straightforward, and what we're seeing is the heights. So K is the relationship between the force and the displacement. Right. It's a bit clear as mud just now. Apologise. We'll get it there. So, in this scenario, anyone heard of elastic and plastic behaviour before?
Yes.
Good. I love feedback. Otherwise I'm thinking, I've been taught. Right, good. You've got elastic, plastic behaviour. Now, what we can see here in these two examples is the stiffness relationship. You know that how stiff it is from this equation here is very different, or i.e. the slope of the angle is very different. Or, in other words, I've taken my ruler, I've hung a weight onto it. The first one, the load is a load, but it's not destroyed my ruler. But unfortunately, we put more load on, it's pulled it, and it's became like plasticine. Right? My ruler is stretched into that plastic range. And now it's no longer as stiff as it used to be. Now it will continue to just become like glue tack or plasticine. So the stiffness is then gone, but it will start to fall down. And that's what that's talking about. Right. In real life, when we build buildings, we don't take a universal beam or a universal column, big steel girders. We don't take those and design them to work in the plastic range. We design to work in the elastic range. That's what we want to do. So, in this scenario here, we're looking at the viscoelastic behaviour. My comment I said 2 seconds ago about what we don't want to do, we're still looking at the extremes at the moment. And we're looking at S as being time. We're looking at viscoelastic behaviour now. So before it was my ruler having a higher load on it. Now if we say, if I put a load on, and I leave it for a minute, or an hour, or a day, or a year, or 10 years, what happens over time? Viscoelastic behaviour. And so it's the same equation, but we've got the unit of time put on. So the load can remain consistent, but over a period of time, you'll see the stiffness will change. Anyone think of an example where that might happen in real life? You can see that K. We'll come back to those examples in a minute. I've got a few up here. Permanent displacement, elastic displacement. So that's fine. Once you've taken my ruler and you've stretched it beyond where it can go back to normal, after that it's now a buckled mess of a ruler. If I then take the load off and put the load back on again, take the load off, it'll never go back to its original shape. It's bust. Where here, if I put the load onto my ruler and take the load off, it's back to its original shape. It's fine. That is elastic, and that's the plastic range. Fairly straightforward. Right, so this is one example, timber. Timber, if you put a load on a timber beam, point load in the middle of it, and you leave it for 50 years, or even a year, you'll get what's called creep. You'll get sag over time. You can calculate, you can predict what that's going to be. Materials do the same, but timber definitely does it. Any other examples where you might have that? Steel. Who said that? Right. Steel, yes, but not to the same level as timber. Any material would be the same answer. Yeah, any material will have that, but some materials will have it more pronounced.
Plastics in warmer climates.
Plastics, yeah, definitely, yeah. Now, what I was hoping somebody would say, and I was going to call them out on it, but no one did, would be glass. Anyone heard the wives' tale or the rumour that glass, look at the back of the room. Anyone heard the rumour that in Edinburgh they'd done a study in the old buildings that they found that the glass is all warped and twisted. It's because glass is viscoelastic behaviour. Anyone ever heard that? They used to teach that in high school, right? Up until about, I don't know, 7 years ago, I think it was. Someone done a proper study, because nobody really studied that. Nobody cared. People made it up and say, oh, it must be true. So someone actually done a study on it, and what they found was glass does not behave in a viscoelastic behaviour. Right? I'm surprised no one's heard of the myth. What they've done was, they went round these old buildings that are 100, 200 years old. They checked the thickness of the glass, top, middle, bottom, whatever, and they found it just happens to be random. So it'd be thicker at the top, thinner at the bottom, and it's because it's how they blew the glass, how they got those small panes of glass in the first place. So the wives' tale would be glass would be. However, back to that. However, bitumen is an elastic. Sorry, what's the word again? Viscoelastic behaviour. Bitumen does. There's a very famous experiment where someone's put a bunch of bitumen in a glass and it has drips. I'll show you a photo of that in a minute. Bitumen will behave in that manner. Timber, this is another timber one. This is one of my buildings years ago, and one of my students, and we had a building, and this isn't viscoelastic behaviour, but it is elastic behaviour. We had this building set up, and we put loadings on it, essentially pulled that down and pulled that down to simulate what would happen in real life in a worst case scenario. And what we got was movement. We even had a level of slip. So there's an element of movement by slip, but also deformation of the panels as well. Again, it was absolutely tiny, and we could predict what it was going to do, and we could actually test it as well. So this is an experiment of the bitumen. Bitumen's the asphalt on the roads. I think, from memory, this test has a drip come down every X number of years. Anyone have a guess how long it would take a drip for bitumen to do? or it could be what temperature is it. You know, what parameter do you want to put on it? I don't know too much, so it took 10 years for the first strip to fall into the glass. 8th strip fell on blah blah blah. So that's quite nice. That experiment's been running since 1927. I don't know too much about it other than here. I would imagine other factors would control influence that. So think of materials aren't just static. Temperature, moisture content, all sorts of things have an influence over the material. Right. In most cases, linear elastic behaviour to failure can be assumed for the rod. Right, let me rephrase that. For our rod and for everything that we do in the real world, we are going to assume that the linear elastic behaviour up to failure is correct. That's Hooke's law. Hooke's law took something quite complicated and said, like, up to failure, it's got any failures there. After it's failed, it will still take a load, but it will no longer take the load. Sorry, an example would be my ruler. I start to pull it down. It's not failed yet, but once it starts to go into plastic range, it's physically failed. It will no longer take the same volume of load. I'll still take it at load, but it's deformed, it's already failed. So up to failure, up to that load there, we assume that the behaviour is a linear elastic approach. However, we're never going to build using Fmax. Fmax is the ultimate limit state. We're always going to build within that 10-40% we're going to do. So within that, we're going to assume that everything that we do from now on in our career, it will be in a linear behaviour is what we'll assume. Therefore, F equals K over L and delta. K, we still don't know what K is yet. We do know that KL is the stiffness of the bar. Okay. Right. K is a constant value. Well, we know K is a constant value because of this assumption here that we're going to assume it's a linear elastic. Assume. We know it's not perfect. We know it's not that very first statement on my very first slide. We know it's not a perfect model, but we know that it works. Right? We know it works well enough. What is the value? If you're taking notes, what I want you to write down, I want you to write down this equation here first of all on your paper. Just do it. That'll be your first one. That equation 1 if you want to number them. Next thing you want to do is to write down what these mean. Stress and strain. We'll be using this so many times, you'll just need to know it. Right, stress. Stress is force divided by the area. So the stress is my surface area of my hand pushing down on that. If I know the force and I know my surface area, I know the stress I'm putting onto that surface area, yeah? Makes sense? Strain. Strain's different. Strain is the elongation divided by the original length. That is the strain that's put on. The two are quite different. Strain is the elongation, the distance of elongation divided by the original length. So that's the strain that's happening in this member here due to that force. The area is just area. So the stress strain curve you probably recognise that and think, oh wait a minute, that's just the exact same graph you had before. You just renumbered, you re-identified it. Of course it is. Stress-strain relationship are very similar. So indicating the ratio, stress over strain is equivalent to E. E is the modulus of elasticity. You'll have learnt that before in first year. You get E in first year?
Yeah.
You did, right. So that's one of the things you probably studied E before.
Last module.
Right.
Last semester, but
I hope so anyway.
and some stuff previous many
Yeah,
years
of
ago.
course, of course. Right, so Young's modulus is what it means. Now, unfortunately, Young's modulus, it's called so many different things. Right, it's called E, MOE, Young's modulus, all the same thing. All depends who's ever standing up talking. They might call it something different. But E, just the modulus of elasticity, or Young's modulus. Young is who came up with it originally. So the force displacement relationship is F, same thing, can be rewritten as this. Tell you what, I'm dying to do this. Hopefully this will work. Eat chocolate whilst using an iPad. It's all messy. I'm hoping this works. If it doesn't, don't shoot me. I go full screen. Yeah, another time. Right. Oh, cool. It does work. What was I going to do there? I was going to do something cool, wasn't I? Yeah, that's it. Right, so we have that, and we want to transpose that. If we write down, now I'm going to do it in two ways, so you can figure out how I'm doing it. I can see you looking at this equation here. Got F. So if I go that is essentially, let me redo that. I'll do it in blue. And I've got this equation. What am I looking at? K delta. Equation there. I'm going to use that one now. So I can go. That makes sense? Those who that doesn't make sense to you, let me do it a slightly different way. Do it in red over here. Hopefully you can see this. F. So F at the top, stress and area at the bottom, and if I want to get what F equals, so I can go F equals that, or if I want what area equals F stress. That makes sense? Right. Okay, cool. So I've got that there. Now I want, like it goes back to blue, I want to take this out and get short of my L's, because that's just saying this. That. See, I've not rehearsed this, have I? Okay. Makes sense. Wait a minute. If I look at that, I can see that there. So I can rewrite that as, I'll do it in red, as EA. We've got K equals EA. Just from manipulating that. All makes sense? So I can then rewrite that top equation as that. Okay. So that's just me doing exactly the same thing, but the shorthand way. So the axial stiffness of the rod is a function of the material properties, the elastic modulus, and the geometry. Geometry being area and the length. So yeah, so that's it. It's a function of two things: the geometry and the modulus of elasticity. You can understand that. That's really what you need for today. Final remarks, which is very similar to what we said at the very first slide, that it is an approximation. It's a very good approximation of how things work in real life. So hopefully with your notes that you've got, we're going to do this first exercise. The time now, we've got lots of time. We've actually got about 40 minutes roughly. We've got two that we're going to do. This will be the first one. What I'll do in the meantime is I will pause the recording so that it's not boring. Unpause. For the recording, for those that are not here, get your units correct first of all. So the blue to the red. Then do all your equations in order. Work out, make sure you've got all your variables sorted in that respect. We now know we have everything for this example, and only at that point do we get the calculators out and make it legible, and we're all fine. Now there's a second way of doing this, which we discussed before. If you got the answer 1.584, then you're absolutely bang on. But the second way of doing the correct answer for this example here is simply the equation F equals that stress-strain relationship, or the stiffness relationship, EA over L. Why is my laptop's not switched on? There we are. So we have F, we know we've got F, we know we've got E, we've got everything, bar delta. We can just simply rearrange that equation, the numbers in. It's much faster, isn't it? So I think some of you have done that method as well. So that ability to manipulate an equation comes to your advantage if you know you can manipulate things in the appropriate manner. quite a lot of what we do in this module, there might be more than one way to solve it. Don't just assume there's only one way. Okay? This is an additional tutorial. This would normally be, you take it away and do it at home. Let's have a look at the time. Time passed. You've got 20 minutes. So why don't we do this week's tutorial in class? Right, we'll give you the answer. Or should we? We'll see. Can't remember now. We'll give you the answer definitely next week. What we'll do is, from next week onwards, I'll give you a portal that you can submit. You submit it, total voluntary, then I'll give you feedback. We do the exact same thing. Write down all the variables that you know that you have. I've got F. I know the sides of the rod, 40mm by 40mm. So I should know my area. So I've got F, I've got my area. I've got my L, 1.6 meters. Steel used. Now, generic steel is always going to be, not always, sorry. I'll be careful what I say. Depending upon the steel that you're using, but a lot of the stuff in our examples will be this number here for normal generic steel. Calculate the final elongation of the square rod. It's applied in that manner. Should take you no time at all. So, see what I'm doing here? I'm giving you the equations as well on the board, so you can then see what you want to manipulate with. Remember, years ago now, I had an exam. Terrible memory, as I was saying before. My memory is terrible. So I literally just sat down the night before the exam and wrote out all the equations multiple times, just so when I went into the exam, the very first thing I did, when I wasn't allowed to touch the pen to paper, was I just wrote out all my equations on one page of the document, and then I didn't have to worry about remembering things. I had it all written down. That was my technique. You can do whatever you want.
Capital G of Jupiter.
What I'll do is I'll give you the answer, but not how to get to it. I'll give you the how to get to it later on. Or is that just rude? Just have a look at what you are signing.
This is a square. A circle. That's why I was doing this. I was like, oh my goodness, like.
Yeah, so the area is just a.
Times height.
It's the same as the length.
It's not a circle. I'll tell you. Is this it?
Is that the answer?
I think so.
Give me the number.
2.857.
Right.
Yeah, it's a square.
You say it's a square, but it looks like a rectangle.
Well, that's why. Well, to be fair, I was thinking length times width times height for some weird reason. I was like, oh, what's that for? Cubic. There it is.
I'm conscious that I've not got the sign-in checking code yet for you. Getting a bit worried about that, so will you give me 2 seconds of your time? Oh, has anyone else got the answer yet? What'd you get?
2.857.
Awesome. You the same? Sure.
At the start I got it wrong because I didn't know if it was a square or a rectangle, but I just realised it's a square.
Aye, definitely.
I'd prefer.
What am I trying to do here? Signing.
40 times 40.
Well, no, mate. Like I seen that, I was like,
I was getting to a head of